The LAWPCA anaerobic digestion and energy recovery facility was built primarily to reduce the volume of solids we had to manage as well as controlling those costs. The facility went online in early 2013. The project was designed by CDM Smith. It was built by Methuen Construction and cost a little over $15 million. We did receive some financial assistance, just about $1.2 million. That came in the form of SRF principal forgiveness, as well as an efficiency main energy grant. We also got the loan at 1%. We estimate the savings are somewhere around $1 million per year, and this is made up primarily in the savings of cost to dispose of the solids. There is some money in the energy that we produce. We do get some tip fees for the feedstocks we receive, as well as the sale of renewable energy credits. The process starts by feeding our primary solids, our thickened waste activated solids, and our feedstocks out to the digesters. We're pumping a little over 50,000 gallons of this material per day. The feedstocks are a mixture of food waste slurries, spent milk, yogurt whey, brewery waste, de-icing fluids, and other high-strength, low-waste solids. We do receive 2 cents per gallon for these feedstock materials, and they are beneficial to the digestion process, as well as help make additional gas for utilization. We operate 2 digesters in parallel. They are roughly 690,000 gallons of storage each. We are operating a mesophilic digester, meaning we've trying to keep these temperatures between 95 and 98 degrees Fahrenheit. There's not a whole lot going on within the digesters other than a little bit of mixing. There's no moving parts. It's basically just full to the brim of digested sludge. When we pump 1 gallon of sludge out, we displace 1 gallon of digested sludge. We're required to maintain a residence time of at least 15 days inside the digester, but we're normally averaging somewhere around 25 to 30 days. These digesters are concrete tanks with fixed covers, and what you see here is about half the tank, which is above ground, the other half being below ground. There are 3 pipes that actually exit the top of the digester in this little cupola area. The first being the sludge overflow. The sludge is filled in the tank to the very bottom of that pipe, so every time we're pumping a gallon of sludge out, there's a gallon of sludge going out that overflow. This is now digested sludge heading to a digested sludge storage tank. If that pipe was to ever become plugged, the sludge would rise and would end up going out the emergency sludge overflow. That is piped to our headworks and something we hope never happens, but is therefore a fail-safe. With the biogas being the lightest, it is piped into the top of the digester, and that is going to exit through a 6-inch pipe and meet up with the other digester gas and be sent into our gas conditioning building. There are a handful of devices on top of each digester. There are a series of pressure and vacuum reliefs, really intended to maintain the structural integrity of the tank if we were to ever build too much pressure or start to draw a vacuum. Each of those systems have flame arresters or flame checks in line, so if a flame was to ever develop, it would prevent it from traveling further down the pipe and causing a larger fire or explosion. If all these fail-safes were not to work for us, there is an emergency gas hatch. It's just a large cover that will pop if we ever exceed 13 inches of water column within the digester. This is the last line of defense, so something we never want to see going off. And we also have a radar level transmitter on each digester to make sure our levels are being maintained, and also to help us during a takedown of a digester to understand that our levels are below the side hatches to make sure we never open a hatch and make a big mess in the yard. On the side of each digester are the 2 sludge lines. There's the primary sludge overflow that's heading to our digested sludge storage tank, and then the emergency sludge overflow. Because that is an open pipe back into our headworks, there's a trap on there. It was originally designed to have a glycol mix in there. We've since started using water, and we have heat traced the pipe. Works a lot better for us. The digested sludge storage tank is holding the material that was digested and discharged out of the two digesters. It's half underground, half above ground, similar to the digesters. The concrete portion is holding the digested sludge, approximately 168,000 gallons. The top portion is actually our biogas storage, so it's a dual purpose tank. The membrane up top is fixed, and there's an inner membrane that is holding our biogas. Because there's not a whole lot happening within the digesters themselves or even the digested storage tank, all of that equipment is housed in our digester equipment building. This building is made up of 3 rooms, one being our heating equipment, the other are our electrical and controls, and then the lower level are all our mechanical equipment, primarily the mixer pumps and feed pumps. Within the heating room portion of the digester equipment building are a series of pumps and pipes, but the 2 most important pieces of equipment here are our supplemental boilers and our heat exchangers. Because the digester needs to be maintained between 95 and 98 degrees Fahrenheit, there's a fair amount of heating that needs to take place to this material. The heat exchangers are constantly being fed material from the digesters, and heat is circulating through that system at all times. The boilers are a backup heating system if we are unable to extract enough heat off our combined heat and power units. The 2 supplemental boilers are dual fuel, meaning they can run off the methane produced from the digesters, or they could also run off natural gas if needed. Ideally, these units do not operate and are only here in place of an emergency or if we had one of our combined heat and power units down. The sludge heat exchangers are operated in parallel, meaning there's one heat exchanger for each digester. The heat exchangers are shell and tube, so essentially a pipe within a pipe. The inside pipe is full of the digested sludge, constantly being pumped and recirculated. Flowing the other way would be hot water from the heating loop system, and the hot water is basically trying to maintain a sludge temperature of the 95 to 98 degree temperature required for the mesophilic bacteria. There are a series of pumps needed to move all of this hot water around. There are pumps that go out to our cogen units to extract heat off the engines. We've got pumps that are circulating through the boiler system. There are pumps that send hot water through the heat exchangers, as well as supplying a handful of air handler units for the digester equipment building itself. Down in the basement of the digester equipment building is where all the mechanical equipment is housed. There are some digester mix pumps for each of the digesters. There are recirculation pumps that are taking material from the digesters and continuously pumping them up and through the heat exchangers. There are a couple pumps dedicated for the digested sludge storage tank to keep that material mixed, and then a series of pumps that are taking the digested sludge and pumping them up to our screw presses. There's some automated valves down in this basement as well as a plant water system. The digester mixing pumps are similar to the recirculating pumps and the digested sludge storage tank pumps. They're all Vaughan chopper style pumps. They've got cutters on the impellers, keeping the material chopped up finely. The mix pumps are operating every time we are feeding material, whereas the recirculating pumps are operating 24/7. We followed the digested sludge around a little. Let's go look at the biogas. As you recall, the gas was coming off the top of each digester through this little cupola. You can see there's not much gas storage here, so all this material is flowing out at approximately 40 to 50 CFM, and it's going to be heading over to our gas conditioning building. You can see that as the gas flows off the top of the digesters, the two digesters are combined before entering the gas conditioning building. Because the biogas can be explosive, we have some gas detection within this building. That gas detection system is tied into lights on either side of the door. The green flashing light tells us it's safe to enter. The red light tells us we cannot enter until the gases have been removed from the space. The pumps here are the screw press feed pumps. They are rotary lobe pumps made by Borger. They're taking the digested sludge material that's been stored in the digested sludge storage tank and pumping it about 400 feet back over into the treatment plant process building up into our screw presses. Similar to the top of the digesters, there are inline pressure and vacuum relief systems as well as flame arresters tied into this biogas as it's exiting, going into storage, and going throughout gas conditioning equipment. The gas enters the gas conditioning building. It's rather dirty, so our job here is to knock out any foam, any sediment, remove whatever moisture we can, as well as things like hydrogen sulfide and siloxane to make this gas good enough quality that it can be utilized. First step in gas conditioning is to go through a foam separator. There's a little solenoid at the top of this tank, and on a preset timer, it's just spraying water and knocking down any foam, and then allowing the gas to continue for additional treatment. Stop is into a sediment trap. It's an angled plate that forces the gas to slow down just enough where any of the heavies will settle out to the bottom and allow the gas to continue for additional treatment. The gas, once the foam has been removed and the sediment dropped out, can really go one of three ways. It can go for additional treatment and eventual utilization. It could be sent to the gas storage membrane or to our flare system. This is all done through common piping. The gas wants to follow the path of least resistance, so it primarily wants to go to treatment. It's being pulled in for additional treatment into a gas conditioning skid. However, if that system is maxed out, all the gas is being utilized, it's going to back up into this piping system and then go into the second easiest path, which is the storage. The last path is our flare, and that has a regulator set at 8¼ inches of water column pressure. So the gas has to basically be fully utilized, then back up, fill up an entire storage tank until the point that pressure builds enough to open a regulator and send it out to a flare. Gas that's going to be utilized passes out of the building into an H2S removal vessel. Inside this vessel we have some iron impregnated wood chips that are designed to bring our hydrogen sulfide levels down below 5 parts per million. Once the gas passes through the H2S vessel, it flows back into the building into our gas conditioning skid. The skid has a couple particulate filters. It is taking the gas and dropping it below its dew point through a heat exchanger system, drops out any remaining moisture. It uses some of that incoming hot gas to heat itself back up, and then it pressurizes itself to 3 to 4 psi, which is the pressure needed to be utilized. Once pressurized, the gas flows outside into 2 activated carbon columns for siloxane removal. The siloxane was not part of the original project, but was added on once it was discovered that the siloxane under the high pressure and temperatures within our engine cylinders was actually forming a silica sand that was really aggressive and causing some detonation issues within our engines. I mentioned earlier, the gas wants to be utilized. It does want to go through additional treatment and go to either the boilers or our engines. However, if we're making more gas that can be utilized, the gas is going to back up and go into this gas storage membrane. The membrane can hold 33,000 cubic feet of gas, which is about 1/3 of our daily production of gas. The outer cover is fixed. There is an inner membrane that fluctuates based on the volume. And as I stated earlier, about 8 inches to 8¼ inches of water column can be maintained in here. Once that pressure is exceeded, this gas will start to flow towards our flare. The outer shell of the gas storage system is fixed using 2 PD blowers housed in the system you can see here. Within the outer membrane is an inner membrane that works much like your water tank at your house. It's going to fluctuate based on gas volume, so we can store up to the 33,000 cubic feet within that tank, or build a pressure of 8½ inches of water column, at which point the gas will back into the gas collection system and make its way to the flare. The waste gas burner system, which most people refer to as the flare, is put in place for times that we have exceeded our utilization. We're making more gas than we can use or store, or times when our equipment is down and we've exceeded storage capacity. The gas has to have some place to go. The safest place for it to go is to be burnt and sent to the atmosphere. So at about 8½ inches of water column within the gas piping system, the gas regulator will open up and send itself over here to the flare. We do run a pilot off natural gas that's always on standby and lit. So with a lit pilot, pipe full of gas, you can quickly get a 10-foot flame. Ideally, we utilize all the gas that we make and send none to the flare. It's often difficult because gas productions fluctuate and utilization equipment's not always available. So when we can, we're taking the gas that's gone through the gas conditioning system and piping it over here into our combined heat and power unit building. Combined heat and power units were manufactured by Tech 3 Solutions. These engines are designed to run on biogas as well as natural gas. They're capable of producing 230 kilowatts of power, and there are 2 of these units. The engines on each of the combined heat and power units are V8 engines with methane injectors. They're very standard engines for heavy loading equipment, and the engine itself is produced from Liebherr. As you can see here, the generators are coupled onto the back of each engine. As I mentioned earlier, each generator can produce roughly 230 kilowatts of power. In order to keep the engines cool, we run a jacket water cooling system, which is a 50-50 mix of water and glycol. The cooling system is circulating the engine and pulling off all the excess heat and sending it back over to the digester equipment building, where we then utilize that heat to heat up the digestion process. The jacket water system within the cogens goes through a series of heat exchangers. This is where we're taking the heat from the engine, sending it into a mixture that is going back over to the digester equipment building and being utilized for the digestion process. The series of pumps and valves on the front of the cogen units are automatic controls telling whether or not there's enough capacity within our heating loop to absorb the heat from the engines. So if the water is cool enough, it can soak up some heat from the engines and send it back to the digester equipment building. And if it's too hot, this is where it gets diverted into a radiator. These are the engine radiators. Ideally, we do not use these cooling devices. Instead, we try to keep all the heat for the digestion process, as well as heating the spaces within the gas conditioning and the digester equipment building. The controls for our cogen units are somewhat sophisticated in that we are trying to produce power that is clean and can sync with utility. So before an engine can ever start producing power back to the facility, it needs to make sure it's within acceptable limits. And there are engine controls as well as electrical controls, lots of sensors and safety devices built into these systems. Once we're producing power off the engines, the power is sent over to a switchgear unit, which is ensuring that the quality is good enough to sync with utility, as well as controlling where that power is distributed within the facility. The electronics in the switchgear is very complex. It is PLC controlled and is ultimately necessary to make sure that the quality of power that those engines are producing is able to be synced with utility. It's also making sure that the power is distributed where it needs to be and that it cannot go back out onto the grid during an outage. So there's a lot of critical operation happening here. We do monitor our output at our SCADA system, and with a max production capacity from the engines of 460 kilowatts, there are times where we're actually exporting power out to the grid. This concludes the virtual tour of our digestion facility. However, we do enjoy giving in-person tours of this system. We're happy to answer any questions you have and can be reached anytime at tpeasley@lawpca.org or by calling our facility, area code 207-782-0917.